Hello, intro to proofs. Thank you guys so much for your just flexibility and letting me do this asynchronously. I'm feeling a lot better now. But yeah, so let me kind of walk you through just an intro to chapter 9, where we're going to talk about sizes of sets. And we're going to really try and build our rigorous definition on what it means to count. Um, so the idea is pretty simple. We all intuitively know how to count, right? I'm teaching my 2-year-old Josiah how to count. And from an early age, we kind of have this idea on what counting is, but I don't know if you ever really thought kind of critically or long and hard about what counting really is. It's just kind of something we intuitively do, which is nice for finite sets. Totally works, right? Finite sets, you just kind of count with your fingers or do whatever, and you can count, and that's fine. But we want a version of counting that works for all possible sets, not just the finite ones. How do you count an infinite set, right? Because you can't keep counting forever, right? It'll stop. It has to. They'll just keep going. So how can we tell different infinities apart? And so that's where we're going to come up with this kind of strange, maybe what seems like a strange definition for counting at first, or how we tell the sizes of sets. But to kind of motivate the example and why it makes sense, let me kind of give you a silly example. And so here's an example. Let's say we have some sheep, right? And so I want to go with my son Josiah and I want to count sheep. And so what do you normally do when you count, right? You kind of assign a number to each one. So he'll be 1, 2, 3, 4, 5, 6. And so I know that there are 6 sheep. There are 6 sheep. And the reason I know this is because I assigned each one a number and only one number. And so another way I could think about this is I kind of have the set 1, 2, 3, 4, 5, 6. And what did I do with this set is I assigned each one of these guys to one and exactly one sheep. And then this right here, when I kind of draw it with arrows like here, this should be kind of reminiscent of something we've done. And if you're thinking this is creating a one-to-one bijection or a one-to-one onto function between a set of natural numbers and the set of things I'm trying to count, then you're correct. Then you're exactly right, right? What counting really is in its essence is we're creating a function, and it actually goes both ways, right? These arrows go both ways. That sheep corresponds to the number 1. That sheep corresponds to the number 2. That sheep corresponds to number 3, 4, 5, 6, etc. And so because each sheep has exactly one number it's accounted for, and each number has exactly one sheep it's accounted for, we have a one-to-one onto function, and therefore there are 6 sheep because it's in bijection with the numbers 1 through 6. And so what we really do in counting is we're associating a set with a subset of the natural numbers, which the natural numbers are 1, 2, 3, all the way forever, via a one-to-one correspondence. Remember, this, another way of saying this is a bijection. A bijection. And so this is actually how we want to count. And the reason is because one-to-one correspondences are bijections. You can have them for infinite sets. You can't really count and give everyone a number when you have an infinite set, but you can put things into a one-to-one correspondence. And so that's kind of going to motivate why we're going to use that definition. And a lot of the lecture is going to seem kind of weird because we're going to prove a lot of things that seem really obvious, but we're going to do so using this definition of a one-to-one correspondence or a bijection. So let's give that definition. And so we're going to start by saying when sets are equivalent in the sense that they have the same size. And so what we mean by that is a set A is equivalent to a set B, provided there exists a bijection. So you need to, if you can show that there exists a bijection from the set A onto the set B, then we say that they're equivalent, and we say A is equivalent to B. Another way to say this is they're in one-to-one correspondence, or they have the same cardinality. And so let's do an example. Are the following sets equivalent? And yeah, right. I can send this guy to that guy. That guy gets sent to that guy. And then this guy gets sent to that guy. And that would do the trick, right? So my f from A to B, such that f of 1 is equal to A, f of 2 is equal to B, and f of 3 is equal to c, right? That puts them into a one-to-one correspondence, and so they're the same. B, on the other hand, is not. B is no, because any function from C to B can't be onto. There's no way I can have one arrow and only one arrow and hit. And so no, and it's because the order of C is 2 and the order of B is 3, and 2 is strictly less than 3, right? And so I'll remind us of what that means, but that's the cardinality, right? The size of the set. How about these sets? Are these sets equivalent in the sense, do they have the same size? So there's 1, 2, 3, there's 10 elements here. How many elements are in here? Well, 1, 2, 3, 60 is 4, 61 is 5, 62 is 6, 63 is 7, 64 is 8, 65 is 9, 66 is 10, right? And so x and y are in correspondence, and we can let g be the function g from x to y could be the function g sends 1 to 57. And so what does g send an arbitrary guy in x? He's going to send it to x plus 56, and that will get the job done, because then if you plug in 10, it gets sent to 66, and if you plug in 1, it gets sent to 57, and it gets sent to everyone in between. And so you need to show that this actually is onto and one-to-one, but it's not hard. I mean, there's 10 things. You could literally just line them up. Let's do a slightly more interesting example. Let d plus be the set of odd natural numbers. Prove that the function from n to d plus defined by f of x equals 2x minus 1 for all x and n is a bijection. Therefore, those guys are in one-to-one correspondence. And so how would we prove that? Well, let's do onto. Let's do the proof of onto. Let, I don't know, let's call it y be an arbitrary element of d plus. So what does that mean? Then y is an odd natural number, so y equals 2n plus 1 for some n in n, right? That's the definition of being odd, because y is odd. And so what guy is going to get mapped? Well, then f sends a natural number to 2 times that number for minus 1. And so what natural number would get mapped to y using this correspondence? And I think what you do, right, if we want to solve for, actually, we could even do better. We don't even have to use the fact that it's odd. Just start with some odd thing, and then we're going to figure out which guy maps to it. So just set 2x minus 1 equal to y. And then actually we just solve for x, right? X would be 1. But actually, I'm going to need the fact that it's an odd integer. So let me back up for a second. So then if we need f of x to equal y, then if f of x equals y, if f of x equals y, that means 2x minus 1 equals 2n plus 1 just by substitution. And then solving for x, we add 1 and divide. So x equals 2n plus 2 over 2. And so that's going to be n plus 1, which is a natural number. And so, therefore, it is onto, right? Let's set x equal to n plus 1, where n is the number that you get from the fact that y is odd. Then it's onto. The fact that it's one-to-one is really easy, but I'll let you practice. So, homework. Or I mean, I guess I would say try for yourself. The proof that that one is one-to-one is not hard. Okay, how about this one? Prove that this is onto, where g is a function from r to the positive given by take a number and raise it e to the x. Why is this one onto? So let's let y be a natural, be an arbitrary positive real number. By the way, this means not 0. So y is not equal to 0. What x is going to map to it? Well, take the inverse. Like if you set g of x equal to y, equal to y, then solving for y, or for x, you take the natural log of both sides, and x equals ln of y, which is an element of R. Why is that an element of R? Well, because y is strictly greater than 0, right? It's a positive real number, so it exists. Then g of ln of y will be e to the ln y, which equals y, and it checks out. 1-to-1. Why is this one 1-to-1? Let x and y be elements of R such that e to the x equals e to the y. Well, then taking natural log of both sides, you get ln e to the x equals ln e to the y. So x equals y, and we're done. And so it is a 1-to-1, and it's bijection. For these two, that's something to point out, is that these sets, n and d plus, they're actually in a relationship, right? D plus is actually a proper subset. So maybe I don't know actually how they do it, but it's not equal to. It's a subset and it's not equal to n. And so n is equivalent to a proper subset of itself, which is kind of interesting. That never could happen with finite things, right? If you have a finite thing and you take a subset of it, a proper subset, there's no way it can be the same size as it, right? It got smaller. But the odd numbers are smaller in a certain sense than the natural numbers, but they're equivalent as sets, which is showing how kind of infinity can mess up our intuition. Similarly here, right? R and R plus, the real numbers and the positive real numbers, they're equivalent as well. And the positive real numbers are a strict subset of R. So again, this kind of idea with infinity is that it doesn't quite work the way we would expect it to work. But that's okay, because we have a definition that still works. As long as you have a 1-to-1 onto function, you are the same. And so that's what we're going to do. And so for the rest of this, we're gonna talk about with finite sets. But before we do that, let me remind us of some things. From chapter 6, section 4, we talked about bijections. And if you have a composition of bijections, then you get a bijection. So if F is a bijection from A to B and G is a bijection from B to C, then their composition is a bijection, which is another way that we're going to use to say that if A is equivalent to B and B is equivalent to C, then A is equivalent to C. So there's this kind of transitiveness of equivalence. Also, if you have an equivalence between A and B, then the inverse function gives you an equivalence between B and A. So you can just take the inverse function, and we're going to use that a lot. Those two things lead to this kind of theorem that we'll use all the time, and I won't prove it to you because the proof is basically just using those theorems verbatim. And this one is just the identity function is the one that would be because what does it mean for it to be equivalent? That there exists a bijection. The bijection between A and A is just the identity function. So for this one, the identity function on A is a bijection from A to A. For this one, F inverse is the bijection from B to A. And then for this one, G composed with F is the bijection from A to C. So that's why they're equivalent, because those are the bijections that get it done. I don't love that. Move that so I can make that a little better. G composed with F is I guess I don't really need the parentheses there. G composed with F is the bijection from A to C. So that's why that one is equivalent. So let's do another kind of fascinating one. So let 0, 1 be the interval of real numbers between 0 and 1. If you have any real number B where B is bigger than 0, let 0 to B. Again, these are open intervals, so they don't include the endpoints. Real numbers between 0 and B. Prove that the function that sends f of x to b of x for all x and 0, 1 is a bijection, and hence the open interval 0, 1 is equivalent actually to any open interval of the form 0b, where b is any number. It could be a bajillion, right? But this function is a bijection. So here's the proof. Again, I'm just going to kind of give a sketch of it, but it's not too hard. The onto, so we need to start with an arbitrary guy, in here and show that we can map to it via that. So let, I don't know, y be an element of 0b. So it's not 0, it's not b, it's some number in between there. How are we going to map to it? Then let x be equal to, I guess, y over b, which is still bigger than 0 because y and b are bigger than 0. And y over b is less than b because if y is less than b, because y is less than b, because y is less than b, and b is a positive number. And so thus, y, oh, sorry, and it's not even y over b isn't just less than b, it's less than 1. I can do even more because y is less than b, and so you can just divide both sides by 1, but divide both sides by b to get that. So thus, y over b is an element of 0, 1, and g of y over b, well, that's going to just be b times y over b, which equals y. So it works. 1 to 1. Why is it 1 to 1? So let x and y be elements of 0, 1, such that f of x equals f of y. Then bx equals by, and so very clearly, just dividing both sides by b, x equals y. Check. 1 to 1 is really simple. So thus, we have a 1 to 1 correspondence, and so 0, 1 is the same thing as a set, meaning the same size as 0b for any number positive number b, which is kind of crazy. Okay. Let's remember cardinality. So I've been talking about it, but just a quick reminder. A finite set, the cardinality of A, denoted card A, or a lot of times I just use absolute values to mean the number of things in it. It's the number of elements in A. And let n sub k be the subset of the first k natural numbers. And so clearly the cardinality of n sub k is equal to k. Then we have some definitions. A set A is finite, or is a finite set, provided it's either the empty set or there exists a natural number k such that A is equivalent to n sub k. So that means that you can put it in one-to-one correspondence with the numbers 1, 2, 3 to k, which makes sense, right? There's some natural number that you can put in correspondence with. It's a finite set, you can count it. A set is an infinite set if it's not finite. So whenever you're trying to prove things, at least for in this homework with infinite sets, use the fact that it's the negation of it being finite. And so just take the negation of your statement. So either the contrapositive or the contradiction of your statement. So because we don't, that's our definition of infinite set is that's just not finite. And finally, or not finally, if you're in equivalence with n sub k, then you have cardinality k, right? Your cardinal number is k. You have k elements. And if you have cardinality 0, that means you're in cardinality. That means you have the same cardinality as the empty set, and you'd say your cardinality is 0. So the end of this lecture, we're going to be spending time proving theorems that seem obvious, but we're going to make sure to use these definitions and make sure that they match our intuition. That's the key, is we want them to match our intuition on finite sets, so that when we kind of generalize to infinite sets, that we know it's a reasonable definition, right? We don't want a definition of sizes to be something that doesn't match our intuition. We want to kind of generalize our intuition. The issue is that if we just kind of say we want to count things and just kind of willy-nilly do it, we don't really have a good way to do that with infinite things. But this idea of using kind of bijections is something that makes total sense in an infinite setting, and it matches our intuition in the finite setting. That's the key, is it matches our intuition. And so we want to use that and leverage that. And so these next couple of results are going to seem kind of weird and really self-explanatory, but we're going to prove them using the definitions. So let's do that. So any set equivalent to a finite non-empty set A is a finite set and has the same cardinality as A. And so how do we prove something like that? So proof, let B be a non-empty set, or let B be a set such that B is equivalent to A. Well, we know that since A is a finite set, since A is finite, A is equivalent to n sub k for some k, right? That's the definition being finite. That was our definition being finite for some natural number k. Whoop. Okay. And so therefore A has cardinality k. So what can we do? Well, we have B is equivalent to A, and A is equivalent to n sub k. And so by theorem 9.1, we can just kind of use transitivity. By theorem 9.1, B is equivalent to n sub k. Thus, cardinality of B equals k, which was the cardinality of A. And so they have the same cardinality, and we're done. It's kind of silly and a really straightforward proof, but the idea is we're using the definitions, right? The definition of equality or equivalence for sets is that they have the same size. Definition of finite is that it's equivalent to n sub k for some k, and then using transitivity. So if B is equivalent to A and A is equivalent to n sub k, then B is equivalent to n sub k. Thus, B is finite. I guess I should say B is finite. So I should say thus, because that's the definition of being finite. Thus, B is finite, and B, the cardinality of B equals K, which was the cardinality of A. So they have the same cardinality, and we're done. All right, let's do another one of these. If A is a finite set and X is not an element of A, then if you take the union of A and X, it's a finite set, and cardinality of A is equal of A union X is cardinality of A plus 1. Okay. So what we're going to do is we're going to build, so there's kind of cases. So what happens if A is the empty set? If A is the empty set, then A union X, the element X, is just the set X, right? It's just the set X. Then the cardinality of just the set X is equal to 1, which is equal to 0 plus 1, right? The cardinality of that. And it's clearly finite and it's great. So we technically have to do that case, but it's pretty lame, and so we're gonna just do it fast. Let's assume it's not. So assume A is not empty. Is not empty and finite. And finite. So what does that mean? Then A is equivalent to n sub k for some k. For some k, natural number, right? It has k elements in it. That's basically what we're saying. And we need to kind of build a map from this to basically k plus 1. If we can do that, then we're done, right? If we can build a map from there to there. So consider the following function. Consider G from A union the element X to n sub k plus 1 given by the following. G is the following map. It's a piecewise. It's I guess we need to give this, we should probably give this equivalence a map, a name, I guess. So let F be the bijection that does it. Let F be the bijection from A to n sub k. Be a bijection. We can do that because they're equivalent, right? So there exists a bijection, and we're just going to give it a name. Now we're going to consider a new map G from A union Xn. It's just going to be F. So it's F. So maybe I should say it like this. G of an element A is equal to F of A when A is an element of A. And it's going to equal to be K plus 1 when A is equal to X, right? Because that's the other guy. So basically send everyone to where they're already being sent, and then send X to K plus 1. It's exactly what you think would be, but this is just a fancy way to write it. But it's very important that we use the definitions, and so even though it seems a little clunky, this is the way to really make sure we're doing it rigorously. Okay, we need to make sure that this is a bijection. So claim G is a bijection. If we can show that G is a bijection, then that would give us that A union X is in equivalence with N K plus 1, and everything would follow through. So let's do the 1-to-1. 1-to-1. So why is it 1-to-1? Let X1, X2 be elements of A union X, such that G of X1 is equal to G of X2. Okay, so there's kind of some cases here, right? Basically, if one of these guys is X, then the fact that these two guys are the same. So I'm going to do it in two cases. Case one, where neither of them, X1, X2, are not equal to X. So they're just in A and they're not X. Then G of X1 is equal to G of X2 implies, but what is G when you're not X? It's just F. And so then implies F of X1 is equal to F of X2 because that's what G does. And then what does that tell us? Well, F is a bijection. So thus X1 equals X2 because F is 1-to-1. So that's case one. The other case is that one of them is equal to X. And so let's just call it X1. So X1 is equal to X. And then X2 is not equal to X because they have to be different. All right, we're assuming that they're different. So what do we get here? Let me add a page. So X1 is equal to X, X2 is not equal to X, and we have G of X1 equals G of X2, such that G of X1, well, what is G of X1 going to be? G of X1 is K plus 1 is equal to G of X2, which is F of X2. But where does F live? F of X2 is some number between, it lives in 1 through K. And so we get K plus 1 is equal to some, I don't know, J, where J is an element of N sub K. But why is that a contradiction? Well, K plus 1 is strictly bigger than any number in here, and that's not possible. So that's a contradiction. So contradiction. Thus, X2, if X1 is equal to X, X2 equals X equals X1, and so it's 1-to-1. So if we have two of the guys that aren't in X, then we use the fact that F was a bijection. If one of them happens to be X and the other one wasn't, but their outputs are the same, that's not possible, and so they both have to be X. And so that gets it done. And so that gives us 1-to-1. Why is it onto? Onto. So let J be an element of N sub K plus 1. How do we map to it? Well, there's two cases. Case one, if J is strictly less than K plus 1, then there exists an A in A such that F of A equals J, right? Because we have a bijection from A to 1 through K, and so there exists an A that maps to J. Then G of A is equal to F of A is equal to J, and we're good, and we're done. So that's how we map. That's how G maps to G. If it's less than K plus 1, case 2, it's equal to K plus 1. If if J equals K plus 1, J equals K plus 1, then G of X equals K plus 1, and we're done. And so in both cases, we're able to hit it. So therefore G is bijection. Hence, A union X, the set X, is equivalent to the set N K plus 1. But what does that tell us? Therefore, it's finite. That's the definition of being finite, is that's in equivalence with subset of the naturals. And its cardinality, the cardinality of A union the set X, is equal to K plus 1, which equals the cardinality of A plus 1. Cardinality of A plus 1. Whew. Okay. So that was a lot. But this idea of kind of how we can make the cardinality 1 bigger is a kind of strategy we'll use later in infinity, and that's why I kind of want to spend time doing this. But it seems a little wonky at first, but this idea of kind of having it match on the first K elements and then just sending the next one to the last one to K plus 1, that's a pretty common strategy we do with these guys. And so that gives us the fact that if you add an element that's not in your set, it increases the cardinality by 1, which is exactly what we'd hope it does, right? So it does match our intuition. Okay, let's try this lemma 9.5. For each natural number m, if A is a subset of n sub m, then A is a finite set, and the cardinality of A is strictly, or is less than or equal to m. And so to do this one, we're going to proceed by induction on m. So proof. So we will proceed by induction on m. So base case. So base case, m equals 1. If m equals 1, there's two possibilities, right? A is either equal to the empty set, or A is equal to the set 1. And in both cases, it's finite. Both cases, A is finite, and the cardinality of A is less than or equal to 1. So that's fine. Okay, how about inductive case? Inductive step. So assume it's true for K. So assume true for K, true for some K in N. So what is the statement we're trying to say? If A is a subset of N sub K, then A is finite and cardinality of A is strictly less than. That's what we could assume. We want to show it's true for K plus 1. So how can we do that? So let's start with an arbitrary guy. Let A be a subset of N sub K plus 1. So start with an arbitrary guy there. We want to show that it's finite and that the cardinality of A is strictly less than K plus 1. But what can we do? Well, we can consider A and take and subtract an element from it, right? There's some element in there. And so just remove one of them. And then now we have a set that has K elements in it. That's a subset of K plus 1. And so we're going to remove K plus 1. If we remove, basically the idea is if you remove K plus 1 from that set, then A is now in N sub K, and we can use the inductive hypothesis on it. So set A prime equal to A minus the number K plus 1. So K plus 1 might not actually be in the set A because it's an arbitrary subset. It's an arbitrary subset of the numbers 1 through K plus 1. But if it is, we'll get rid of it. But in either case, if it's not, then it's just equal and it still works. But what does this tell us? Then A prime, the order of A prime is going to be, A prime is now a subset, of N sub K, right? So by the inductive hypothesis, A prime is finite, and the cardinality of A prime is strictly is less than or equal to K, right? But what is A prime? A prime is, or what is A? A is A prime union K plus 1. But A is equal to A prime union the number K plus 1. And so thus by our previous lemma, thus by lemma 9.4, A is finite, and A prime, the cardinality of A is equal to the cardinality of A is equal, yeah, that works, is equal to the cardinality of A union, because they're the same set, but that's equal to the cardinality of A prime plus 1, which is less than or equal to K plus 1. And so we're done. So therefore, thus by induction, if A is a subset of N sub M, then A is finite and its size, the size of A, has to be less than or equal to M, which is, again, really straightforward, right? If you took, but we're just making sure to use the definition so we have rigorous definitions, or rigorous kind of grounding on why this is true. All right, all of those two lemmas were really to get to this lemma, or to get to this theorem, and I think I'm going to stop after this theorem. So this theorem is really, really important. And again, it's something that seems really obvious to us, but again, we want to make sure we have it on firm footing so that we can use it when we go to the infinite case. So if S is a finite set and A is a subset of S, then A is also finite and the cardinality of A is strictly less, or is less than or equal to the cardinality of S, right? What's the proof? So we should start with an arbitrary subset of A. So let A be a subset of S. Well, we know S is finite. So S finite, so S is equivalent to N sub K, to N sub K for some K in N, because S is finite. And let's let F be the bijection that does it. Let F from S to N sub K be the bijection. I mean, there's lots of bijections. Be a bijection because it's equivalent to it. What's the idea? We're going to restrict F to the subset A, and that's going to restrict to a subset of N sub K. And therefore, and then now that we're in N sub K, we can use lemma 9.5, because A will now be a subset of a set of natural numbers, and then we can use. And that's kind of the basic idea with all these things, is we want to bring everything over, map everything over into a subset of natural numbers, because we know what happens there, and use the rules there. Okay, so how are we going to do that? So let G be a function from A, and we're going to map it to F of A. We're going to let G be a map from A to F of A, where F of A is the subset of N sub K, and A is a subset of S. How is G going to be defined? Such that G of little a is equal to F of A for all A and A. For all A and big A. So the idea is G is just the restriction of F to the subset A, and then its image is F of A. So this is going to make it a bijection. So claim G is a bijection. So why is that 1-to-1? Because F is 1-to-1, because F is 1-to-1, and it's literally the same function. And so it's 1-to-1 because F is 1-to-1 onto. Why is it onto? Well, pick an element of F of A, then by definition there's an A that gets mapped to it onto. So maybe I should spell it out. Let B be an element of F of A, F of capital A. Then by definition, there exists an A such that F of A equals B. But so then G of that same A equals F of A equals B. So thus Thus, G is a bijection. And that means that A is equivalent to f of A. So why did we do this? Well, because we want to basically put A inside a subset of the natural numbers, because f of A lives in a subset of the natural numbers. And so its cardinality is going to be less than the cardinality of S. And since f of A is a subset of n sub k by lemma 9.5, I think, the cardinality of f of A has to be less than or equal to k. And so, but because A is equivalent to f of A, that means the cardinality of A is less than. So thus A, the cardinality of A, which equals the cardinality of f of A, is less than k, and we're done. Less than or equal to k, and we're done. And so any subset of a set has to have at least smaller, is the same size or smaller, and that's now on rigorous grounding. And this leads to a couple corollaries I'm not going to prove, but I'll just point them out. One of them will be a homework problem. If A is a finite set and X is an element of A, then A minus the element X is a finite set, and cardinality of A minus X is equal to cardinality of A minus 1, which means you can subtract 1. And a finite set is not equivalent to its proper subsets. I'll start class with this. I'll start class with this one. It's not that hard. Start class on Thursday with this. Because the reason why this is so important is because this is what exactly we'll use to define what an infinite set is. An infinite set is going to be one that you can do this. So finite sets are the ones where you cannot be equivalent to any proper subset. Infinite sets are going to be precisely the ones where you are. And that's going to be how we characterize infinite sets. All right, I'll assign you guys some homework, and I'll see you guys on Thursday. Thanks.